The next speaker is Salomão from University of São Paulo. He will talk about on the existence of open book decompositions for rib dynamics on the tight tree-sphere.
Okay, thank you very much for the invitation. Special thank to Leonardo Maccarini. In fact, this talk will be a continuation of what Humberto was talking, and the setup will be very similar, but it will be in a slightly more general case. Okay, so again, the motivation to study rib flows on spheres are to understand the Hamiltonian flow in a star-shaped energy level in R4. And so we can consider in S3 a contact form which is just a multiple, a function times the standard contact form in R4, which is lambda naught there. And if you just multiply by a function, it's equivalent to study this Reb vector field to study the Hamiltonian flow in a star-shaped energy level. So f is just a positive function, and this contact form lambda naught is tight. So again, in S3 we consider the Rib vector field or Reb vector field, which is just given by the contraction of the vector field with d lambda is 0 and contraction with lambda is equal to 1. So the vector field is in the kernel of d lambda, and it's normalized by 1. So we consider this vector field. Okay. So we look in S3 for global sections. As Humberto has explained, this is just, in this case, we look for global sections which are of embedded disks in S3, and the boundary of this disk is just a periodic orbit, and the interior of the disk is transversal to the Rib vector field, and it has the property that every other orbit will hit this embedded disk infinitely many times, backward and forward in time. So we look for this type of dynamical simplification to study the dynamics in that energy level as a diffuse of the first return map in that energy level, which simplifies a lot the study of the dynamics. So this example was discussed last talk, which is not only the existence of a global section in that energy level, but the existence of a foliation. So if you have this periodic orbit here, which is just represented by this dot, these two dots here, it's like a transversal cut, and you have this periodic orbit, and each leaf, so you have a foliation in the complement of the periodic orbit in S3, and each leaf and each leaf of this foliation is given by a global surface of section. So we are not just looking for global sections, but in fact by this what we call open book decompositions of the flow. So let me just give an idea of the Conley-Sender index. in general, you can take a periodic orbit, which is represented this by P, and then there is some way to define it, but very easily speaking is just how nearby orbits will turn around the given orbit. So in fact, this would approximately be the number of half-laps. If you look at the linearized flow over that periodic orbits, then this linearized flow will just have a winding number, and this approximately, the Conley-Zender index will be half of this, of the number of laps that the linearized flow is moving in that given period. And this of course represents how nearby orbits will turn around that orbit. And of course we need to take a very special way to measure that, very special frame to measure this index. So again, the setup is S3 with the tight contact form, F lambda naught. We have the contact structure, which is given by the kernel of this form, and we consider the symplectization of S3. And the problem is that we are trying to find this open book decomposition as the projection in S3 of those finite energy planes. So we study these pseudomorph curves, we project them in S3, and this gives the open book decomposition. So to talk about these special curves, we put an almost complex structure in the symplectization, which is just take the R direction and the J of this, the delta A, which is in the R direction, is the Reed vector field. And this implies that the contact structure, which is inside the S3, is preserved by the So we consider this a Riemann surface in general, and a map from this Riemann surface to the symplectization, which is complex linear and has finite energy, as was explained before. It's a very important notion of energy. I will not put this definition of finite energy of what it means, but the important thing here is that this map from the Riemann surface to the symplectization is defined up to a finite number of points called the punctures, and then the study of this maps to the symplectization are very related to periodic orbits. As Humberto said, that near each of these punctures, if not removable, they will approach periodic orbits, in fact periodic cylinders over the periodic orbits. And if you assume some other hypothesis, like if the contact form is non-degenerate, there is a very nice formula on how this curve approach each puncture, how it goes, how it is asymptotic to the periodic orbit. So we are looking for this type of open books, this foliation in S3 minus a periodic orbit, which are projections of finite energy planes. So finite energy, non-zero means not constant, and it's finite means that exactly what I just said, that near each puncture it's very stable, it behaves very, very well. This function this energy was in fact discovered by Hofer, and he proved Weinstein conjecture in some cases for using this fact. So I will mention again this result of Hofer, which is for contact forms which are dynamically convex, which means that the Conley-Sender index of all orbits are at least 3. And so we have, in any case, for any contact form with this hypothesis here, we have this open book, this foliation. And each foliation is a global section for the flow. And of course, I have to mention this recent result by Umberto, which is that the fixed point of the return map, which is just here by this red circle, this fixed point also admits this open book decomposition, which is a transversal open book. There might have a lot of dynamical implications by the existence of this open book. So let me say that this orbit here has index 3, and this in general might have index greater than 3. But in any case, this open book still exists, which is transversal to the original one given by Hofer, Vysotsky, and Sender. No, no, there is just the rib flow, and it's transversal to both foliations. But it could have something dual, but they have the same properties for the rib flow. So let's now discuss something about the more general cases. He gave the example where the star shape involves the dynamically convex, which is, for instance, it includes the hypersurface which are really convex. But as I said in the beginning, this study here could work also for star-shaped energy levels. And more different things could show up. And let me give you an example. So there is this more recent theory about these finite energy foliations in S3, which was given by also Hofer, Vysotsky, and Sender, which you can also foliate S3 as projection of finite energy curves. These curves could be planes, could be cylinders, and well, the easiest case is the open book given by disks, as before. But here we could find what they prove is that in the generic case, assuming that lambda is non-degenerate, that every periodic orbit is non-degenerate, we could have something like this, which an orbit of index 2 appears here in the foliation. So if you see, what does it mean? Again, it's just a slice of the foliation. We could imagine a line through here and rotate this picture around this line. We would have this more precise what it's going on. So if we look this orbit of period 2, which is represented by these 2 points, we can have this plane asymptotic to it, and also and this other plane, and inside here it gives you a 2 sphere, and this inside here we have an orbit with index 3, and this leaves are very similar to the leaves of the open book decomposition as before, and they are foliating all the inside here. And these leaves here could, for instance, they in this case they break when you approach this plane. They break as the sum of this cylinder connecting the index 3 periodic orbit and this plane. This could be the general picture. For instance, it's very easy to build energy level of these types, which are, for instance, if you pinch the energy level, something like that, you could have something very similar to this picture. And the periodic orbit here, which has index 2, is hyperbolic. In fact, it's in this case, it would have very small action. And in each side of this, those planes are very nearby here, and in each side you would have all this filling, which would behave as if it were dynamically convex. For instance, it's possible to build something like this, and which has just this orbit with index 2, and outside it's dynamically convex. But what this example is saying about this example is that something is changed, because we don't have the surface, global surface of section anymore. So the question is, when do we have? So what could we do with this example? So could we still find an orbit which is the boundary of an open book decomposition, or this is the maximum that you can do? So this is another example which is also interesting, because this foliation, you have also an index 1 orbit, which connects to this piece here. And here we have this index 2, which is always hyperbolic. This index 2 periodic orbit is always hyperbolic. And here there is a small picture on how the unstable and the stable manifolds of this orbit. This index 2 must be hyperbolic, and so the unstable and stable manifold, they are independent with those leaves which are approaching. Here we have the cylinder connecting index 2 to index 1. We have this other cylinder here connecting index 3 to index 2. And inside here we have a one parameter family of cylinders connecting index 3 and index 1. And the flow, just all the leaves are transversal to the Rib vector field. And this kind of a different example of what is happening. So the question is, what happens in the general case of a star shape? Does it always when can you find this open book decomposition with an orbit in the boundary? So this could be a question, and we try to answer this question in this. So if we look back at the open book decomposition, this is the orbit here, and we have the leaves, and all the other periodic orbits are linked to the given binding of the open book decomposition. The question is this is necessary, of course, but is it sufficient, for instance, for you to find? So let me just give an example. Given an unnoted periodic orbit, we can say that this another periodic orbit is linked if the homology class of this orbit in the complement of S3 to P gives a non-zero element of the homology. So then we say that the P bar is linked to P. So if you take any surface binding P bar, it would have to intersect P. Okay, so let me state this theorem, which is joint work with Umberto Rinievich, which deals with the more general case, which is like, suppose that you have, in the dynamically convex case, these orbits here with index 1, they never appear by assumption. So now we have the hypothesis that given this orbit with index at least 3, which is a candidate for the binding of an open book, we will assume that all the other orbits, looking just at these orbits with index 1 and 2, they are linked to that given one. And at least now we assume also that lambda is non-degenerate. Maybe it's possible to avoid this assumption, but still, well, at least in some cases we can do it, but still has some problems. So let's assume that all the orbits of index 1 and 2 are linked to that given orbit. We have just to check, in some cases we have just to check a finite number of orbits, because in some cases these orbits with index 1 and 2, they have low action, so they show up in a finite number. So we just need to check these orbits here, and so P, the candidate for the open book, has index at least 3, self-linking number -1. And all the orbits are linked, then the theorem is that this orbit here is in fact the boundary of this open book decomposition. So, and so what do we get with this? So this open book, each leaf of this open book decomposition is a global section of the flow, and it gives 2 or infinitely many periodic orbits, which is a conjecture of Hofer, Vysotsky, and Zender, that all star-shaped carries 2 or infinitely many periodic orbits. It's not proven in the general case. Well, I mean in R4. It's proved like in the convex case, as Umberto talked about this a lot, because of the existence of the open book. And it's proved, for instance, in those previous cases where I said, in a more generic case where you assume transversal intersection of stable and unstable manifold, it's also proved infinitely many periodic orbits. But in the general case, it's not proved. So in fact, it goes in that direction. I have to mention that also the existence of this orbit with index 3, self-linking number -1, and linked with all these orbits with index 1 and 2, these conditions are also necessary for the orbit to be a candidate for the binding of an open book. For instance, you could not have an orbit with index 1 or 2 or less than 3, which is the boundary of an open book decomposition. So these conditions here, and of course, if it's the boundary of an open book decomposition, they must be linked, and since the vector field must be transversal, it's possible to compute that this index also must be -1. So these are, in fact, necessary and sufficient conditions for an orbit in S3 to be the bound of the open book decomposition. So we assume this is the non-degenerate case. I think I'll try to give an idea of the proof of this theorem, which is very similar to what Umberto said, to the methods that Umberto did in his thesis, which is we start with this orbit. We have the orbit, and we know some properties, some topological properties of this orbit, and we try to produce this open book decomposition. So first, it's possible to show that this orbit here, which is unknotted, so there is an embedded disk boundary coinciding with its image, and the characteristic foliation of this disk must have just one singularity, which is real elliptic. Which looks like a node, a different language for describing, classifying this singularities of. So we call it real elliptic. It looks like a node, and the nearby it's nearby the boundary, which coincides with the periodic orbit. The vector field is transversal. There is this estimate with this disk has finite d lambda. We don't know if d lambda is always positive in this disk, but the L1 norm is finite, and this will give compactness for that. The Bishop family. So the picture is very the same that Umberto said. So we have this disk, which is represented here in the 0 level or in the r direction, and from nearby this the elliptic point of the disk, we have this family of disks appearing, and they have index 1, unparameterized index 1. So they are in a one parameter family, and we see what happens when these disks are when you look at what happens with this family of disks when you go to the other side. From one side it goes to the elliptic point, from the other side we don't know what happened. So there are some calculation that this disk cannot touch the boundary of F, which is this disk here. It's a very tricky computation by Hofer, Vysotsky, Zander. This family cannot just touch the boundary because of some intersection constraints. So it must break. So you cannot. This family here cannot be compact. So it bubbles. And when it bubbles, we have this bubble tree with a finite number of these curves, which could be something like that. The first level, we have this starting at 0, could show up some negative punctures. And in each level, we could have some kind of something very similar with other curves. And these curves, they have some particular properties, like they have just one positive puncture and could have an arbitrary number of negative puncture. So the the analysis now is just to see that this family of bishop disks they break. They cannot. It's not a compact family. They will break, but they will not break until hitting in the limit the boundary of the disk, which is the periodic orbit. So let me try to. This is the first level of the bubble tree, which is in fact an embedding. For generic J, we would have this type of estimate with here the Maslov index of the positive boundary, and here the Conley-Sender index of the negative punctures, and this should be like that, the number of punctures. This must be non-negative. So we have this estimate, but the problem of this estimate is that this guy here, could have negative Conley-Sender index here. Could be negative. So you could have many negative punctures, maybe with negative Conley-Sender index. So this could be a problem for using this kind of estimate. In the other levels of that bubble tree, we avoided using the Fredholm index because of some transversality problem. So, in fact, we are just allowed to use this estimate. Well, in the other levels, we could have some curve, which is very similar. So, but we have this small lemma, which is, suppose that you have here an index m, which is positive in this level here. The positive puncture is m, which has index m, which is positive. Then there should be one of the negative punctures should be less or equal than m, the index. They cannot be all of them above m. And this is an estimate using this invariance, which Umberto talked something about them. And of course we need to analyze each case separately and suppose that m is positive and d lambda, the energy of that curve, is positive. So we have these indexes in some type of transversality of this curve with the contact structure. These curves are not tangent to the Rib vector field. It has in fact, some transversality with the Rib vector field, so we can use some index. And so the positive index, this number, which is the wind infinity, which is how the curve approach the limit, how it winds around the limit. So if the Conley-Sender index is 2k, this number must be at most k. And you see the negative eigenvalues of that asymptotic operator that Umberto said. And for the negative punctures, you have to look at the positive eigenvalues of the asymptotic operator. And so if you assume by contradiction that the Conley-Sender index is above m, then it means that this winding number here must be at least k minus 1. So this is now it's kind of a very simple computation. We have this index wind pi, which counts some numbers of some zeros of pi du, which is the zeros of the curve projected to the contact structure. there is this relation between this invariant and the others. And so if you just use these estimates above here, you would get a contradiction. K minus 1 minus the number of negative puncture, K, is above, at least 0, but here it's at least 1, so it would give a contradiction. It would be K minus something, at least 1 times K. This would be a negative number and not non-negative. So the number would be, this should be 0, but it's not the case. We are assuming by contradiction that all negative punctures have that property. These other cases, it's kind of a little bit more complicated. That if d lambda area, which is the area of the contact structure, assume is 0, then this curve must be a branched cover of a cylinder of a periodic orbit. It must cover the cylinder some way. And so there is some way to estimate, because you have just one positive puncture and many negative punctures. And so the sum of the covering numbers in each negative puncture should be the same as above. And this makes the Conley-Zender index less than the one above. So this. Oh, okay, yeah, okay, yeah. Okay. So in the beginning, if we use again this estimate here, that in each level you decrease the number, the Conley-Zender index, in each level you decrease, or at least you keep the same number, then you cannot have any index 1 in the bubble tree. If there is one index 1 in this bubble tree, then this index 1 you could trace the path and find a plane with index at most 1, a plane. And so this is not possible. This is not possible to have a plane with asymptotic, positive asymptotic limit with index at most 1. Also a result by Hofer, Vysotsky, and Zender. So the index must be at least 2 for all those asymptotic limits of the bubble tree. Must be at least 2. So let me just go back to this, and if you now use this again, this estimate again, assuming that the bubble tree has index, the bubble tree has an orbit with index 3. If you just use this again, you will again get into a contradiction. So the index of the bubble tree must be always 2. So we could have a bubble tree with index 2, but now here comes the hypothesis, because we assumed that all the orbits with index 1 and 2 are not linked to the orbit above here, which is the boundary of F. So these orbits here with index 2 must be geometrically distinct from this, from above, because from above we have an orbit which is simple covered with index at least 3. So they cannot be the same geometrically. So, but they have planes which cannot intersect this orbit the way it was constructed. So here comes the hypothesis, and so it cannot happen. So what it means? It means that this bishop family cannot break before reaching the boundary. It must continue. There is no space for it to break. Otherwise, you would produce something like that. In general, you can have, but we are assuming we don't have this orbit within index 2, which is not connected, which is not linked to P. Okay, so in the end, this family goes to the boundary, and a very similar analysis, and using this fact here, which was proved by Humberto, and using this, and this is very crucial, and the bubble tree in the end must break very similar to the dynamically convex case. It must be a half cylinder from 0 to minus infinity, and the disk connecting this is at least 3, it's the same orbit. And this is a plane, well, this is the same orbit here. So it's the same thing, at least 3. And there would be this plane here with positive asymptotic limit, the given orbit. So in fact, this plane is a global section, and so we are now allowed to use all the Fredholm theory that Humberto said, that to perturb this plane nearby, and also again using that all the orbits with index 1 and 2 are linked to them. This family here will not break before. Will not break, and it must be compact. So we have compactness with that linking hypothesis. It will not break. So the family is in fact compact. It's an S1 family in S3 when you project in S3. And these indexes, I have to mention here that this implies some type of approach of. So how do we prove that this disk here is in fact a global section of the flow? This is transversal to the vector field, but could not be a global section. So you take an orbit. So we have this foliation. In the end, we have this foliation of S3 minus the orbit. So you take an orbit, and this will just run over this family, this one parameter family, and how can we say that this given an orbit which is not the periodic orbit in the boundary, it will touch infinitely many times. So we flow the orbit, and if it's far away from the boundary, then it will flow in an open and closed set of this S1 family. So it must cross infinitely many times. But if it goes to the boundary, if the orbit approaches the boundary of the disk, which is the periodic orbit, then it's slightly different. And what gives the possibility to prove that, in fact, if the orbit approaches the boundary, it will hit this plane infinitely many times, is that this winding number is 1, which gives how this plane is approaching the orbit. It's winding. It means that in a certain referential frame, it's winding just once, but the index of the orbit is at least 3. So it means that the flow nearby is winding half lap. At least one, a little bit more than one once when it runs over nearby the orbit. So index at least 3 means that nearby orbits will hit infinitely many times this disk with this kind of approach. So it's in fact a global surface of section, and all these planes we obtain are in fact global sections, and finally we have this open book decomposition. I should say something about geodesic flows in S2 that, so as was said before by Umberto, you can lift the geodesic flow to a real vector field in S3. So you can take the Sasaki metric and contract with the geodesic vector field. It gives a one form which restricts to a contact form in the unitary tangent band. And so there is this double cover of S3 to the T1 S2, and so you can lift the one form which will give a tight contact form, and you can study the geodesic flow up in S3. So there is this result, Harrison-Paternai, that the curvature is between 1 and 4. It's dynamically convex. So this is a simple example of an ellipsoid. Sorry, it's missing something here. And so it's if the sphere is round enough, then when you lift to S3, the flow is dynamically convex. But if you stretch the surface, it might not be. And this is the case, for instance, if you take this ellipsoid and you stretch in one direction, the equator, suppose that it's a surface of evolution, the equator will have low index because the curvature there will be low. So a low curvature means here low Conley-Center index. So this type of surface is very interesting to study because there is some way to relate the size of an orbit, the action, in fact, with the Conley-Center index very easily, because there is this nice referential frame where the linearized flow is monotonic. So, given the argument given by this equation, and so you can measure, you can give an estimate for like if it's too long geodesic, closed geodesic, the index must be high. But if you stretch enough, then the curvature in the equator will be low and the index will be low. So it could be that this orbit here has index 1. It could be. So let me just give this example, which is a surface of evolution. You stretch it enough such that this index here, suppose that this is a short geodesic, and you stretch it such that the curvature is very close to 0. The index will be 1. And the meridian here, which appears in a one-parameter family, it's degenerate, but it has index at least 3. So the flow here is if you look at this, the geodesic flow in the surface, it's always winding around if you don't take a meridian, it's always winding around this direction here, this axis here. And this winding implies that all orbits which are, well, in fact, all orbits are linked in S3. But to talk about S3, we need to be very careful here, because pi 1 of the tangent, the unit tangent bundle of S2 is non-trivial. So there are non-contractible orbits there, and we need just to cover twice to make it contractible. So you can lift it to S3 for contractible orbits. So you always have to consider double cover of the orbit. So it's very well known that when you have a convex surface, convex S2, you have those simple closed geodesics, and each simple closed geodesic gives rise to a global section of annulus type using the Birkhoff global section, which is in fact an annulus connecting the geodesic and the opposite direction of the geodesic, taking all vectors between one and the other. But they are all the same in this characterization, but when we lift them to S3, they are not the same, they are very different. So in this case, we have the equator with index 1 and the meridian with index at least 3. And all orbits are linked to this one, but not all our orbits are linked to this. So in this case, we should have, when we look at in S3, this orbit, the double cover would satisfy the hypothesis of that theorem, would be the boundary of an open book decomposition. So the meridian would be the boundary of an open book decomposition, but not this guy here. This is very different when you lift. And but there is just an observation that, in fact, this case is degenerate. But if this case is we can deal with, it's not a big problem to deal with this degenerate case, because it's possible to control things because we have this positive frame where the linearized flow is monotonic. But this index 1, so, is never the boundary of an open book decomposition when you lift. And this is an example of a non-dynamically convex tight contact form which admits an open book decomposition, because there are these orbits with the index 1. In fact, we could use also this orbit here with index 1 to produce some other orbits. It's the same procedure, doing the bishop disk, taking that disk, analyzing the bishop family through that disk, and producing an orbit, and looking at how the bubble tree breaks, it will produce an orbit with index 2, which by the linking property is not, by the bubble tree construction, must not be linked to the index 1 orbit, which is here. So this is an example of an orbit of index 2, which is not linked to the index 1 orbit. You can like contract. It's possible to see in the unitary cotangent bundle. You can contract this red orbit here, never touching the index 1. So this is really different. The question is, okay, in this case it's really non-dynamically convex, but you still have this open book decompositions through other orbits. So in those previous foliations that I showed, the question is, even if the foliation given by Hofer-Vysotsky-Zehnder is that complicated with orbits with index 1 and 2, is it possible to build an open book? Is there this special orbit with that which links to these particular ones? So this is one question that we cannot still answer. To give an example of a tight contact flow in S3, which you cannot find this orbit. You cannot find this special orbit, which is the binding of the open book, even in the non-dynamically convex case. That's it.
Is there a question or comments? Okay, let's thank Bento again.